Hi guys, welcome back to my channel. Today we're going to be summarizing the different kinds of transformations for a variety of different graphs that we've looked at over the course of the term. So we've had a go at linear functions, quadratic functions, some higher order polynomials, exponential functions, hyperbola functions, and some circle relations. So I think it was Eddie Wu who once said that if there is some sort of geometric relationship, so in other words, if there's some sort of transformation or dilation or reflection that's occurring, then there has to be some sort of algebraic relationship that's underpinning that geometric transformation. So what does this actually mean? Well, what it means is that those transformations such as dilation, reflection, and then the horizontal and vertical translation, they have some key features between all of those different graphs that we use in the formulas. So let's go in and let's do a specific example. So a dilation is when we increase or decrease the size or the slope of our particular shape. So for example, if we had a linear function, a very basic parent function here, y is equal to x, that's going to have a diagram that looks something like that. If I was to increase the size of this slope, so in other words, I was to multiply this by some value that was greater than 1, then that would make my graph a lot steeper until eventually the point it would reach almost a vertical line. As soon as it hits that vertical line, however, that slope is undefined. On the opposite hand, if I was to decrease this value, so decreasing to a fraction or a decimal of some sort, then that would decrease the slope and decrease to the point of being flat when a is equal to 0. So we can also see this in a quadratic function, and I've got the diagram here drawn as well, but just to show you, if I've got my very basic parent y is equal to x squared function here, if I was to increase the value of a so that a was larger than 1, that's going to increase the slope of my line. If I was to decrease that, then that's going to decrease the slope of my particular quadratic. And we can see this in a lot of the same graphs. So we have a polynomial function, so x to some power, so for example, like a quadratic or a cubic or a quartic, we see the same thing. If we have an exponential, so we're starting off with a very basic exponential, y is equal to 2 to the power of x. If I increase that value, then this is going to become a lot steeper. And if I decrease this value, say it was like 1.5 to the power of x, that's going to decrease the slope of that particular function. So again, I'll repeat what I was saying before. This geometric relationship is really underpinned by that algebraic relationship. And for us, that's our dilation factor. So that's this factor A here. And we can see that in a lot of these graphs. So that's going to increase or decrease the size or the shape of our particular functions. All right, so another transformation that we have is a reflection. And again, there's a really common key feature here that's happening with the horizontal and vertical reflections. And that is that we are making that dilation factor a negative. So we're changing from a to negative a. So with linear functions, we start off with our slope, y is equal to ax. If we were to make that a negative, that's going to flip that in the opposite direction. So that's a vertical translation, or vertical reflection. Same thing with the quadratic. If we have our happy parabola, we've got a positive value for a, and if we were to change that to a negative, it flips our parabola. This is the same thing with the polynomials. Now, exponentials are really interesting because they have two kinds of reflections. So we've got our parent function here, so y is equal to 2x. Now, if we were to flip that graph, we can flip it either vertically or horizontally. So if y is equal to negative 2x, that's taken all of these values and flipped them to become negative. So it's flipped them across that x-axis, so in that vertical direction. Alternatively, what we can do is we can flip horizontally so that it's flipped across the y-axis in that horizontal direction. We can also see this with hyperbolas and with, not so much with circles, but with hyperbolas we start off with our parent function and we can reflect and we can flip that function by making it a negative value. So again, this reflection factor is a key feature of these graphs. The last two types of transformations that we have are the translation, so the horizontal and the vertical translation. And again, there's some key features, and this is common to all graphs, and that's the addition of this factor d on the end, because this factor d is really just shifting these graphs up or down. So I've got my parent function. Oh, sorry, this is for the quadratic. I should move that down here. So I've got my parent function. If I was to add a value on, that's going to move my graph upwards. And if I was to subtract a value, that's going to decrease or drop my graph downwards. And we can see that again with our linear equations or with our exponential equations or our hyperbolas, and even with our circles. It's just for circles the transformation is slightly different. But this translation factor d is always going to move my equations up or down. Same thing with the horizontal translations here. So in this case, the horizontal translation factor is this factor c, and that's going to move my function to the right or to the left. Now for linear equations, this doesn't happen so much because we can just manipulate that variable by moving this up or down. We don't really see that so much in slope-intercept form. But for quadratic functions, we can see this. So if we were to have x plus c squared, remember that's going to move it in the opposite direction to what we think. So that we see this graph here where it shifted it to the left. If we had x minus c squared, that's going to shift the function to the right-hand side. And the same thing with the rest of these polynomials and exponential functions is actually the opposite of what we think for this translation factor, for the horizontal translation. So this is going to move it opposite to what we think. So when we have x take c to the power of n, that's going to move our function to the right. When we have 2 to the power of x take c, that's going to move our exponential function again to the right. So again, we're starting to see all these algebraic relationships that are underpinning each of these different functions. So really what we want to do, or what we want to be able to do, is we want to take a function, we want to be able to use these transformations, and we want to be able to sketch the graph without having to rely on a table. Okay, so let's say that we have a particular function and I don't actually know technically what the shape of this function is. I mean, you could probably have a guess that it looks like a cubic function, but I can't make that assumption because I don't actually know. So what I want to be able to do now is I want to be able to manipulate and transform this function without actually having to use a table or without having to use any values. So let's start off. We've got this function here, and we want to use this function to sketch the value of p of x plus 1. So we know, since this is just an addition of a value on the end, that's just the addition of the constant d. So all we're going to do is just to draw that exact same graph, but we're going to shift it up 1. And I'm going to attempt to copy this as best I can. That wasn't great, was it? Let's try that again. So a bit more, there we go. That's a little bit more similar to that original function there. So all I've done is I've just shifted that entire graph up by 1. If we have a look at b is actually a pretty similar question. So this time we're subtracting d, and so all we're going to do is we're going to move this function down 2. So that's going to go down by 2. So this is going to become a lot lower there. And again, this is a pretty rough sketch here. All right, next question, y is equal to negative px. So remember, when we had that negative value, that's the reflection factor, so it's the mirror image. So we're completely flipping this graph over. So this is going to look a little bit interesting. So we've got that starting off there, we've got our hill, we're going back down, and then we're coming back up. So that would be the graph of negative p of x, because we've flipped this function across that x-axis. Lastly, we've got y is equal to 2px. So this is again related to our dilation factor a. So all we're going to do now is we're going to increase the slope of our function because this value here is greater than 1. So we started off with this little bump. We're going to make this bump a lot more pronounced now, so a lot steeper. So it's a little bit hard to draw, but it should be the same shape. It just should be a lot steeper than what it was. So that's our graph of 2p of x. All right, so let's have a go now at this second question. So consider the sketch of y is equal to p of x shown at right. So again, we don't know any other information about this function. I'm assuming that this is probably some sort of polynomial again, but again, we don't know any additional information. So again, sketch the graph of y is equal to px plus 1. So all we're going to do is we're just going to shift this graph upwards. So I want you to have a go now at drawing that in your book. Next, so that's when we move d, so d is going to be positive. Next we have y is equal to negative p of x, and again, just like we saw in the previous example, this is our reflection factor. So I want you to have a go now at sketching this graph in your book of this reflection, right? Lastly, we've got y is equal to p of x plus 2. And when we saw this transformation, effectively what we're doing is we're adding 2 to each value of x. So we're moving this in the horizontal direction. So again, I want you to have a go at sketching this particular function in your book. So pause the video now, and I'm going to come back with the solutions and you can check your work. Okay, so here are our solutions. So for our first one, we've added a constant on the end, and so that's associated with the vertical translation, so we've just shifted this entire graph up by 1. This graph here, we've got the negative out the front, which is indicative of a reflection across the x-axis, so a vertical reflection, and I've just flipped my graph over in that direction. Lastly, we've got px plus 2. So in other words, we've got, let's say that this was a function, if I had x cubed as my particular function, so p of x is equal to x cubed, then if I had p of x plus 2, everywhere I see an x, I'm going to replace that with x plus 2. And I've still got to cube this function. And so this is associated with the change in c. And so this is a horizontal transformation. And so I've shifted this by 2 to the left, because the horizontal is always the opposite to what we think. And so this is now touching at -1 rather than touching at 1 where it was. So I want you to go through and I want you to really get familiar with these different types of transformations and what they look like for different functions such as the linear, quadratic, cubics, hyperbolas, and circles, and so on. All right, guys, I'm going to leave it there and I'll see you in the next one. Have a good day.